I am Alexey, ClickHouse developer, co-founder. Nice to see you all here. Let's talk about the latest addition in ClickHouse, the new JSON data type. But first, let's start with the facts. ClickHouse is the fastest analytics database. There is a benchmark, open source benchmark, available at benchmark.clickhouse.com. It contains about 50 different systems contributed by the community, by the authors of these systems. And you can see that ClickHouse is the fastest among production analytical databases. Let's first review why. What makes ClickHouse the fastest analytics database? It has true column-oriented storage. So let's look at the example. When we create a table with a bunch of columns and a certain primary key, every column will be stored separately. And when we will read, when we will do some query, it will read only specific columns. And also it will parallelize the query execution across the ranges of these columns using all available CPU cores. So the query pipeline looks like this. And if we have even more CPU cores, we will use even more threads. We will parallelize query even more. We will use available CPU instructions, CMD instructions, to process this data efficiently. Now let's talk about the new data type. The second fact is that ClickHouse is the fastest analytical database on JSON data, on semi-structured data. Let's take a look. What is the challenge making it this way? So the new JSON data type, its usage is pretty simple. You can create a table like this. Here it has just a single column with the type JSON. And you can insert any type of data, arbitrary, like API responses, JSON logs. You don't even have to manually look inside this data. You don't have to analyze data types, analyze what is inside this JSON, because ClickHouse will do it for you automatically. But the documents can contain anything, arbitrary data types. And first, let's look at how to not solve this problem. So how this problem could be solved, but not in the best way. One of the possible ways is just to store every JSON as a string field. So let's take a look how it will work if we do it this way. If we read just a subcolumn from JSON, then we will have to parse all these JSONs. We cannot read a subset. We will have to read the whole strings, parse, and only then process this data. Maybe you are using this way to work with JSON today, but this is not the optimal way if you use the latest ClickHouse version with the new JSON data type. Okay, so here are disadvantages. We need to parse it. It is not fast. So let's take a look at the new true column-oriented JSON storage. ClickHouse will analyze different paths inside these objects and store them separately. Sounds simple, sounds easy. And it maintains the same performance as if you manually analyze it and created separate columns for all these data paths. It sounds easy and it should work well. So what is the challenge? It should work as well as with full data types as separate columns, it should work well, but actually it is not so easy. So if you analyze all the columns and define data types, you can have only a single data type for each column. Like in this example, we have one column of int64, another nullable string, another array. And when ClickHouse stores this data, it stores it in separate data files. And for some complex data types, it can use multiple data files. Like for arrays, there will be two files, one with all the values inside arrays and another with array sizes. For nullable data types, it will store a null mask and the values of non-nullable fields. But there is a challenge. If you have real-world JSON data, you can have thousands of different subpaths, even unbounded number of different subpaths, so we have to deal with it somehow. And there could be different data types in different objects for the same keys. And also, some keys could be rare in the data, so this approach will create a lot of different files that will be very sparse. So let's take a look how not to solve this. And let's suppose your JSON has keys from A to Z in different records. And we could create different data files, but then there will be too many different data files. There will be too many buffers in memory to read this data. It will be difficult to write. It will take a lot of time writing this data. So we have something slightly different. And now let's take a look at another problem. So we have a bunch of JSON documents. And the key A has type integer in first three objects and the type string in another object. And somehow we have to store it. And now there is another object with the array data type. How to unify these data types, and do we need to unify the data types at all? Maybe we will just unify all of them as a string. So what shall we do? Let's take a look at another challenge. Rare keys that only present very infrequently. So in this example, we have keys A and B and key C that is present just in a single object. Okay, so let's solve all of this, and let me show how to solve all these challenges. The first solution is another new data type, named variant data type. Variant data type allows storing different data types inside a single column. So you define it like here. Variant of int64, string, and array of int64. And this data type is capable of storing any of these internal data types. Let's take a look how it is implemented inside. So inside the storage, we will have different data files for every data type. One for int64, another for string, another for array. And also we will have one additional file named discriminator. This discriminator will contain the index of the actual data type among sorted data types. And it also supports nulls for free. So the discriminator 255 is reserved for nulls. Let's take a look. And in memory, we also maintain the offsets inside each column. So when we need to locate some data, like we need to locate where is row number 3, how to read it. We will look at the discriminator column, then look at the offsets, find the corresponding subcolumn, and read the data by the corresponding offset. Okay. And it also solves the problem of sparse values, so they will be only the present values will be stored. Okay, it looks like it solves challenge number 2, type unification. Instead of type unification, we just store every different data type. We don't unify data types. If we have integers and strings and arrays, we will store integers as integers, strings as strings, arrays as arrays. Let's look at another challenge. The problem is that the number of data types can be not known in advance. There could be a large variability inside the JSON. So our next solution is another data type named dynamic. What it is? It is similar to the variant data type, but you don't even have to declare the different internal data types. It will store anything. So the column of type dynamic can store values of any data type. Let's take a look how it is implemented. It contains yet another subcolumn named dynamic structure, and it will encode the list of actual data types. It will also encode statistics for all the subcolumns. The number of data types can be very large, so there is also an option to limit the maximum number of data types stored separately. And if this limit is exceeded, like in this example, we specified max types equals to 3. And actually we have the integer column, the string column, an array of integers, and also we have date column. So, and we also have Boolean columns and arrays of strings. We will just put all these values into a separate column containing like everything the rest. So the first 3 will be in dedicated subcolumns. Everything else will be collected in another like kitchen sink. Okay, so we have the dynamic data type, and it solves the first challenge: how to store many files for highly dynamic, highly variable data. Okay, now about the JSON data type, how it works. How does it work? So let's suppose we have this table with a single column of type JSON. It can be as simple as you see above, or you can specify some parameters like the limit on maximum number of paths, the limit on maximum number of types inside a single key. Let's take a look. So the first is the maximum number of keys stored separately. By default, it is 1024. The second parameter, max dynamic types, is 32 by default. Also, you have an option to explicitly clarify the actual data type for some specific path in JSON. If you do it, it will be stored exactly as a separate column, without variant, without dynamic, just as a separate column of this data type. And you can skip some paths from JSON if you don't want to store them at all. If a subset of your JSON contains like a PI data, you just specify to skip it. If it contains like unnecessary data, any sort of garbage, you just skip it. Okay, so let's take a look at this example. We have a JSON data type with key A contains an object, and subkey B is specified as explicitly as uint32 data type, another subkey as a string, and we limited the number of dynamic paths. How will it work? Let's take a look how it is represented. So the explicitly specified subkey is represented by just a normal subcolumn with explicit data type. Now we have dynamic elements, and they are stored as a dynamic data type inside. We have a discriminator, we have offsets, we have different subcolumns for every data type. And as we have more than at least three different types, some of them will be collected into a separate file. Okay, now let's take a look at yet another subcolumn, and now it exceeds the maximum number of dynamic paths. And for this subcolumn, we have to collect all the remaining subpaths and store them separately together, just to not multiply the number of files. It will be limited. And we have another file containing the rest of subcolumns. So the question is, I introduced all these data structures, all the files on disk. The question is it fast? And you know what? It is. ClickHouse ClickHouse is actually the fastest analytics database on JSON. How do we know? We have another benchmark named JSON Bench. You can take a look at this open source benchmark, jasonbench.com. We tested ClickHouse together with some systems having native support for JSON, like Elasticsearch, MongoDB, Postgres. And we also received some pull requests from community. And there are systems like SingleStore and Victoria Logs and greptimedb added by our community. And you see we are the first. Not just the first among general purpose analytical databases. We are even faster than specialized databases for JSON logs, like Victoria Logs at greptimedb. We are faster than, it's not a surprise, but we are faster than MongoDB. What did you expect? We are faster than Postgres, DuckDB, SingleStore, Elasticsearch, whatever. And the actually, this scale is logarithmic scale. So, and we are the only system that does not do unification of data types. So if you use whatever, maybe Postgres or single store, it will try to derive the common data type. So if you have like int 8 and uint 16, probably the common data type will be int 32. But we don't do unification, we just store everything as it was. So you can reconstruct the original JSON data. ClickHouse is not only the fastest, but also the most precise storage for this data. Every other system loses some information while storing this data. Let's take a look at some numbers. So if we compare to MongoDB, we run a query in milliseconds, 400 milliseconds in this example, and MongoDB does it in 16 minutes. So we are 2,500 times faster. But not only this, we are the most storage efficient database. So in this benchmark, it contains 1 billion of JSON documents from the social network named Blue Sky. These JSON documents are quite large, quite convoluted, but we spent just 92 bytes per document. MongoDB, with the same compression algorithm, takes more than 1.5 times more. And what is also interesting, if we just take all this JSON and put them in the std, so like data.json.zstd, if it is a plain file, ClickHouse still compresses it better, about 20%, because of better column-oriented storage. So ClickHouse is not only the fastest database, it is the most efficient storage for JSON. If you have a bunch of JSON documents, you might think, let's just compress them, but the most efficient way is to put them into ClickHouse. Let's take a look at the storage numbers, and again, ClickHouse is the best. Postgres takes at least 6 times more. I don't even want to count. ClickHouse is the best, period. Okay, now let's take a look at the first query from JSON bench, aggregation on the entire data set. And ClickHouse does it in 400 milliseconds, but also uses less than 3 megabytes of memory. Elasticsearch takes 5 seconds to process this data. Not bad, by the way, but not good compared to ClickHouse. DuckDB will take more than 1 hour, and Postgres will take more than 1 hour. So, ClickHouse now has the best support for JSON. It provides true column-oriented storage for semi-structured data. And it does it better than even storing them compressed in compressed files. It is easy to use. Just do create query, your column, JSON. It is flexible. It is the best implementation among any database we know. And it is 1,000 times faster than any existing traditional data stores. And since the latest release, 25.3, which we released in March, it is generally available. It is production ready. So install the latest ClickHouse version, start using JSON today. Thank you. Any questions?
You find like corner cases where how nested the JSON is?
Probably the worst example. Yeah. Did I find any unusual corner cases that will break this JSON data type? Probably the worst use case is when you have values inside keys of JSON. Like what will happen if you put just a random number inside the key and insert a billion of these JSONs. And you know what will happen? It will work. It will be not so efficient, but it will not break the system. We provided a way for it to work even if the limits are exceeded. Like we store first 1,000 paths separately, and then we continue to store everything else.
Yeah. Are those columns special in any way? Like, can you use them in order by, for example, or?
Yes, you can use JSON in order by, but not the whole JSON, a specific subcolumn. Yeah, a typical example, you create a table with JSON and you have a subcolumn with timestamp. So you just do create table, order by whatever data, dot timestamp.
Were those benchmarks as well-formed JSON or pathologically non-client?
The question is, do you expect well-formed JSON or pathologically what?
Benchmarks where you're comparing performance of the various variables and the ability to take some were those well-formed following a schema, or were those just random?
So first of all JSON are valid JSON, but your question is not about that. These JSON are quite complicated. So, for example, the depth of them is actually not limited. So there is some limit inside these billion JSON documents, but we saw the structure like whatever message.content.entry.message.content.entry, and this repeating, I don't remember, so probably almost 100 times. And it still works. Yeah, so the question is, if you don't use JSON for analytics, does it make sense to store it in the new JSON data type? Let's compare it. So in one example, you will store this JSON just as a string, and let's suppose you never query it. Only maybe use it for auditing, for rare queries. It is still better to use the new JSON data type because it will compress the data better. Actually, it will be slightly slower on insert because it will have to analyze, it will have to split it into subcolumns. But from the data storage perspective, it is way more efficient. So the question is about the difference in performance of insert. Inserts of the new JSON data type will have to spend more CPU to parse these JSONs, to analyze them, to actually spread the data across different files. It will take time. So in certain scenarios, if you're very limited by CPU on inserts, maybe you can store JSONs as a string, but then you will not have a chance to have a pleasure working with the new JSON data type.
When the client requests JSON, how long? It's coming serialized on the server, or?
It depends on the protocol. If you use ClickHouse client or any language client supporting the native protocol, such as our Golang client, it will be serialized also in subcolumns and reconstructed only on the client side. But if you use the HTTP interface, and requested a format. By the way, you can request JSON in a JSON format and it will work perfectly. It will be reconstructed on the server side and sent as JSON. The question is, if you use the JSON data type, do you have to worry about the existence of variant and dynamic data type? No, they are building blocks, and you just use the JSON data type and don't worry about dynamic and variant at all. But we intentionally made these building blocks available because they are usable on their own. For example, you can use the map data type with a string key and dynamic value. It is not like full JSON data type. It does not support nesting, but if you don't need nesting, it is a nice solution for your problem. You can create arrays with a variant data type, and you can store heterogeneous data inside these arrays. The question is about Iceberg and how does the JSON support interact with Iceberg. What is interesting is that Iceberg does not have a native JSON support. Iceberg data format and Parquet as well does not have good support for semi-structured data. So either use merge tree, or if you use Iceberg, you can use it for importing data. You can store JSON as a string in Iceberg, but probably only to import it into ClickHouse. Nevertheless, even if you use JSON in a string, you still can use SQL JSON functions like JSON extract, JSON value, etc. to analyze this data. The question is, as we have some data stored more optimally and some data is put into the shared file, will it change over time if the distribution changes? It can happen during merges. We also store statistics about the distribution of this data. And if I recall correctly, the decision can be changed during background merges.
Are different shards going to have even different distributions of the columns of the data planned this way?
Different shards can have different distribution of data types and paths stored in separate columns, but different replicas will store byte identical data as usual.
So once the nature of the data changes, there'll be some kind of rebalancing of the internal structure. Is that correct, or is that something else?
Yeah, this is correct. So all this data structure is defined and decided on a data part level. And we do merges of these data parts. And during merges, we write a new data part. So we can make a new decision about what goes separately, what will go into dedicated files. Okay, so many questions. I'm really happy to receive so many questions. Thank you.